to the organizers for this very nice workshop, and all the program has been lovely. It's very nice to be able every once in a while to see again all the researchers and friends of the field and just fun talking about math together. So, Kubota-type formulas and support these measures. You might be wondering what it is. So let's start with some. Okay, this is a joint work with together with Daniel Hoge and Fabian Mussnig. You can already find it on the archive if you want. So let's start with some preliminaries. So we work for now with non-empty convex sets in Rn. And we start by studying, introducing the surface area measure of a convex body, which is just we consider the UK is the generalized cosmon. We just consider a sub or a subset of the sphere. We just take the reverse image of that and we measure it. It's just a piece of the boundary of K where the normals are contained in omega. Okay, another notion that we need is the one of Minkowski sum. So this we're familiar with. We just take all the possible sums between the elements of the two sets. And what happens when we consider an interaction between the surface area and the Minkowski sum? Well, this is, you might call it, it's sometimes called polarizations, but it's the same thing as the Minkowski formula for the volume. So we will have, so this is a measure, so we will have a polynomial now, a polynomial expansion in the dilations that we use for the sets K1, Km, and we have these coefficients, which are called mixed surface area measures, and this is at the core of what I will try to present. Okay, another thing that we need, so this is might be the connection with this program. So sometimes it's needed to consider recover from the knowledge of the measures of the projections of a set other informations on the set itself. And so, for example, one thing that we can do is we consider all the possible projections. So, and this is with a hyperplane, but you can fix other dimensions, and then you average the measures of these projections to obtain something. We will get there in a second. And actually, this something is explained by the so-called Kubota formula. So just some notation. This is just classical expansion. So we just consider the addition with a ball and these J intrinsic volumes. And actually, this can be proved in many different ways. But for example, Heidegger's characterization theorem is a quick way to do this. So we, as I said, we consider the average of the projections on subspaces of fixed dimension J, and then we have a normalization term, and this is just, again, the J's intrinsic volume of the original set. And so, just this will be useful for later. We can still express these as something involving these mixed surface area measures. Actually, these are even more particular ones because these are the J. Okay, and so let's get a bit further into this. So we can consider these mixed surface area measures just as this functional, which is linear in each one of its entries and its measure valued. And as an example, as I was saying before, if we just consider the polarization with balls, and so we have coefficients in the polynomial expansions, and these are the so-called Jth surface area measures, which already one might wonder, both for these more general ones and for these easier ones, can we characterize the support of these measures? Because if we go back a second, like these even intrinsic values, one of the simplest things we know, can be expressed in this way here, and understanding, for example, monotonicity properties of this object or other geometric properties. So we have an integral of this is just a support function, but we could consider other continuous function against a measure, and understanding the support of the measure lets us understand us, for example, as I said, the monotonicity, but even other relevant properties. Okay, and just some quick example. When we have the surface area measure, this should be actually n-1, sorry, of a convex set, then the support is given by the extreme vectors. Extreme vectors are just unit vector such that the corresponding reverse image to the Gauss map is just either a face or still whatever point we get back, we can go back again to the Gauss map. So we want the unit vector to be just the unique unit vector at a certain point on the boundary, and these are known as extreme vectors. There is a conjecture, still open, on the general behavior of these mixed surface area measures, which, I mean, this slide will be a bit technical, and excuse me, but it will be necessary to understand what's going on. So the conjecture is that the support of these mixed surface area measures is given by these K1, these Kn-1 extreme vectors. What are these extreme vectors in this general setting? So first we need the definition of touching cone. So I made a drawing for this. So we have, still may read it? Yes. So if we have a point on the boundary of a convex set, we can consider the normal cone. And if we start from a unit vector, we can go back to the face containing this vector, and then we consider the face of the normal cone such that the vector we have chosen is inside the interior of that face. What does it mean? So if we start with something easy, so we have a facet, the normal cone is just one line, and if the unique unit vector that you can choose, it will be just inside this line, so that touching cone is just this, one-dimensional cone. If we go to an edge, for example, well, we have different options, like we have this whole angle of possible unit vectors, and so it depends. It might be in the interior of this cone, it might be on one of the facets. And it becomes even more general when you have a vertex, then you have many other options can arise, so you have either in the interior of the cone, in one of the facets, or on one of the edges of the cone. So there are many different possible combinations on how this thing can happen. And what does it mean now to be a K1, Kn-1 extreme vector? So for we have Z, and we consider the touching cone for each one of these sets, and basically we want a nice interaction between the dimension and the position of this touching cone. So this will mean, actually, this should mean, at least according to the conjecture, that then this vector is actually giving a contribution to the mixed surface area. So, and this is just something to take home or as a rule of thumb for each one of these sets. We have a corresponding facet given by a normal vector, and then we want the interaction between these facets to be nice enough, because this could be expressed even by some similar condition on the facets. Okay, this was the bad part, the rest should be easier. So why do we care about the support of these mixed surface areas? Well, this is important in order to understand the extremal cases of the Alexander-Frankel inequality. Since Alexander-Frankel inequality is involved with mixed volumes can be expressed as integrals on the sphere of a support function, and then we have mixed mechanisms. So that's the original motivation. Some history. So Schneider, even before the conjecture already characterized the support of the mixed surface areas, the Jth surface area, so we just consider all the possible bodies are just either the body K or the ball. And there he introduces the concept of what is and then the support of this is basically its Jth extreme vector, which is a generalization of what I was saying before about extreme vectors, but it's a similar concept, but we won't get into that. And for example, understanding that implies the inclusions of the support, which then gives some monotonicity for example, intrinsic volume. So this is one of the ways that one can really use these properties. Then it took some time to discover something new. So there is this beautiful paper by Scharfen and Van Andel where they're able to tackle more complex problems. So either they have the ball or a tuple of body, such that these are either smooth or zonal, meaning just sum of segments. Okay, and then a bit later, Hug and Reichert generalized this. Instead of zonoid, one can consider even polyoids, so it's just one considers some lower dimensional convex set, and then just consider sums of these things. So now we get to our contribution. So in Rn we consider just the orthogonal basis, just to give some notation, and we consider L the hyperplane orthogonal to the last coordinate, and we consider the unit ball inside this hyperplane. And this is the set for which we that we can include in these mixed measures, and which it's the first time at least that we're able we can actually consider this kind of stuff. You might wonder why we are considering these sets, and this will be clear in a few slides. We have motivation for this. And our result reads like this. So what have we done? So K is fixed. So it's in a sense it's actually similar to what Schneider already did, but instead of considering a full dimensional ball, we consider a lower dimensional ball, which seems easy. It's not that much. Because then the support function, one would like to work with the support functions of these convex sets, but the support function of a lower dimensional ball is incredibly pathological when one reaches certain points in the sphere. To do so, we go through a Kubota-type formula. So this is a bit weirder than what I showed you before, that the original Kubota formulas are obviously way more elegant, but something similar is happening. So here we have, so this some notation we will call a small l, the line through the last coordinate, so it's orthogonal to the hyperplane capital L, and we consider the k+1 dimensional subspaces containing L. And then what we do, well, we consider the projections of the set. This formula is general, like the result is just for a fixed state, but this formula is general, so we have k1, kk different sets. We consider their projections, we average on the projection, and we obtain an integral involving the sets k1, kk, but then the dependence on the average just is switched to this dependence on this term here. And how does one use this? Well, one can represent the support of this mixed measure as the closure of the union of all these smaller, like these are way easier because this is like the top degree surface area measure of K, of the projection of K. But for these area measures, we understand them, is the result by Schneider. These are the support of this one inside the subspace E are just the extreme vectors of this projection. So averaging on these, knowing the local information given by this part here, then we just test all the functions that we want on the sections of the sphere, and then we go to the ball itself. So this is the main strategy. What I will do is show you a quick idea on how to prove this result now. So we need two lemmas. The first one, which starts to explain why something lower dimensional appears, is the following. So if we have this mixed surface area measure, then as much, for example, if you're familiar with a projection body, but plugging inside a mixed volume, a segment then gives you the measure of the projections. And so a similar thing happens when plugging in a segment inside the mixed surface area. So this bigger surface area just becomes this, we just lose one entry here, we go one dimension lower, and instead of considering the set B that we want to measure, we take the intersection of B with the intersection of capital E, where capital E is orthogonal to small e. And this is the first lemma that we will need. The second one is a characterization of some kind of evaluations if you want. So Minkowski additive just means that psi of k plus L is equal to psi of k plus psi of L. So it behaves nicely with respect to the Minkowski addition. And in case we have a functional which is Minkowski additive and continuous, then if we average this functional evaluated on a segment on the whole sphere, we always obtain psi of the ball itself. So it's some sort of characterization of mean width if you're familiar with this kind of language. So what's the idea of the proof? I will just do the case k equal n minus 2 because then the other cases can just be proved inductively. So this is the thingy that we had on the right-hand side. So first thing, we express this Grassmannian, since now the dimensions are nice enough to say, okay, this is just a ball up to some renormalization, and this one is a bigger ball intersected with a suitable hyperplane. Then we use lemma 1, because we are precisely in the case where we have the surface area measure of these projections, and we obtain this. So we switch from the lower dimensional ball to a higher dimensional ball, and now we have this segment inside here. But now we are averaging on this surface area measure including the segment. One can prove this thing here is a Minkowski additive and continuous, and then using the second lemma I showed you, one just recovers precisely, like, so if you are averaging on the subspace L, because this is what we're doing here, like these are the subspace, the hyperplane that contain L. So we are basically not considering all of them. We are just taking the segment and we are rotating it on a subsphere, and then if we add them all together, this is just a subdimensional ball. And this is how, very generally, one proves this result. And as I said, then all the other cases for K just follow from this identical procedure, but just iterating this idea on other subspheres. Okay, so now I will switch quickly to the functional setting. This will be clear in a second. So let's go for a second to the world of complex functions. We're interested in two particular families, the family of supercohesive complex functions. These are just functions that go to infinity quicker than linear. And then we consider the further subspace of the functions that have compact domain in this set here. So the domain is just the set where the function is defined. What do we do with this? Well, there is an analog of the surface area. One can consider it, morally speaking, an analog of the surface area measures for bodies, and for functions, these are just the MongeAmpere measures. So instead of considering the Gauss map, the reverse of the Gauss map, one can consider the gradient of the function, and then we just measure the images of the gradient of the function. Subgradient in this case, in a generalized case. Then we have an equivalent notion of addition, which is the intimal convolution, but this is just, in geometric terms, the Minkowski addition of the epigraph, and in the same identical way, one can describe the multiplication, and then again, we have this polarization formula, which works in the same way as the one for surface area measures, but instead one obtains these mixed MongeAmpere measures. But the concept is similar. We're just switching from integrating on the sphere to integrating on a ring, but geometrically what's happening is the same thing. And okay, just by duality, this remark might be useful later. This formula works even for pointless addition. So from functions we would like to go to bodies. Why? Because these MongeAmpere measures, we will see in a second, can actually be expressed as surface area measures. How can we do that? Well, if we have first we can go to from convex bodies to convex functions. We just take a convex body and take a part of the boundary which can be a maximal part of the boundary which can be represented as the epigraph of a convex function, which will have compact domain because A is compact. Then, conversely, what we can do, we start from a function with compact domain, and then we can just cut the epigraph of the maximum. And this is again a convex body. So nice to notice that in one direction this is reversible. So if we take f, we consider the corresponding body, and then we take the function representing the body, we obtain again f, which is good to know. Well, so this is when I was previously talking about duality, I was implying the Fenke-Legendre, the duality given by the Fenke-Legendre transform, which sort of behaves as polarity for convex bodies. And for practical reasons, we will consider now dual MongeAmpere measures, but it's nothing too fancy. It's that we have f, and we consider the MongeAmpere measure of the Fenke-Legendre transform of f. The nice thing that happens, and this is sort of the core of the strategy, is that we can represent an integral on a N of mixed MongeAmpere measures through an integral on the lower open half sphere of some transform of the original function, and the surface area measure, the mixed surface area measures of the functions of the bodies representing the function. So we have this way of translating one expression for function with an expression of bodies. Okay, but you might still be wondering, why are we doing this? What's the motivation behind this? And we are interested in specific functionals called functional intrinsic volumes, studied by Colesanti, Ludwig, and Mussnig, so which generalize the concept of intrinsic volumes. So intrinsic volumes can be characterized as valuations. We have seen before the definition of valuation in one of the previous talks, which are continuous, translation invariant, and invariant under rotations. Something similar can be done for convex functions, and one obtains these expressions which seem a bit aggressive, right, written like this. But if you think about the previous lemma, now we might have a chance of understanding what's going on. And mind this, here in these mixed MongeAmpere measures, instead of a ball, we have the indicator function of a ball. But consider that this is a ball. The function lives as a convex set, lives in a Rm+1 through its epigraph, and instead the indicator function of a ball, the ball in this case lives in Rm. This will be useful in a second. I'm almost over, don't worry. So, using this formula now, we would like to express the previous functional as something for bodies, just to be able to play a bit around with it. And as I said, notice that if we start from a convex body in Rn, now Rn being the domain of our convex function, which again, though, it's something in Rm+1. If we take the body representing in Rm+1, the set representing the indicator function, this is just the same set, but leaving as something lower dimensional in Rm+1. In particular, if we do this, then we just obtain, these things commute nicely here. Which means that if we consider the indicator function of this ball as a function on Rn, and we use the same lemma as before, here we will obtain a ball of dimension n, but we are integrating on the unit sphere of Rn+1. So this is the motivation. Now from these, the same integral formulas that I showed you before can be written now for these functional intrinsic volumes, and then hopefully this is something that is done already in the paper, but we're still working on that. Then more properties of these functional intrinsic volumes could be understood. And that was my time.